Welcome to today's paper reading. Today's paper is titled, Physics of Language Models, Part 3.3, Knowledge Capacity Scaling Laws. This paper, submitted for meta-internal review, explores the scaling laws of language models' knowledge capacity by Zeyuan Allen-Zhu from Meta/Fair Labs and Yuanzhi Li from Mohammed bin Zayed University of AI. In this study, the authors explore scaling laws that relate the size of language models to their capabilities. Unlike previous studies, they estimate the number of knowledge bits stored by a model. They focus on factual knowledge represented as tuples, such as USA, capital, Washington, D.C. Through various datasets, they establish that language models can store 2 bits of knowledge per parameter, even when quantized in 8. This means a 7B model can store 14B bits of knowledge, which surpasses the combined knowledge of English Wikipedia and textbooks. The study also examines how factors like training duration, model architecture, and quantization affect a model's knowledge storage capacity. The research focuses on the scaling laws of large language models, which are crucial for predicting the performance of extremely large models. Established scaling laws discuss the optimal training flops versus model size, but recent studies challenge these laws, showing that training smaller models with more flops can yield better results. Another key question is the ultimate performance a model can achieve with sufficient training. Traditional theory suggests that scaling up model size can enhance memorization, improve generalization error, and better fit complex target functions. However, these results often overlook large constant or polynomial factors, leading to discrepancies from practical outcomes. This paper introduces a principled framework to examine the scaling laws concerning model size versus its knowledge storage capacity. It is intuitive that larger models can store more knowledge, but the exact relationship and the constant of this scaling are crucial for assessing the efficiency of transformer models and knowledge storage. In this section, we introduce the fundamental concept of knowledge representation as a tuple consisting of a name, an attribute, and a value. For example, the tuple Anya, birthday, October 2, 1996, illustrates this structure. The complexity of a knowledge set is influenced by several factors, including the length of the value string and the diversity of the vocabulary. To quantify this complexity, we define a set of hyperparameters, N represents the number of distinct names, K is the number of attributes, and T is the vocabulary size in a tokenizer. The BioD dataset is generated with fixed attributes and random sampling for values, which allows us to derive an upper bound on the bit complexity required to describe such a knowledge set. In this section, we discuss the 3-bit complexity lower bound. The key idea is to evaluate the knowledge stored in a model using cross-entropy losses rather than average losses. Specifically, we define 3 types of losses: loss name Z for generating names, loss value 1 Z for generating the first value, and loss value Z for generating sequences of values. Theorem 3.2 provides a lower bound on the number of model parameters, log 2, W, which depends on these loss functions and several parameters including N, K, D, T, and L. In the ideal case scenario described by Corollary 3.3, if the model can generate names with exact 1/n probability and values with 100% accuracy, the losses for names and values become 0, leading to a simplified lower bound on log 2, W. This analysis is crucial for understanding the capacity of the model in terms of its parameter count and the accuracy of its outputs. The empirical capacity ratio R, F, and the maximum capacity ratio Rmax, F, are defined based on parameters such as N, K, C, D, L, and T. These ratios are crucial for understanding the model's performance. The scaling laws show that the peak capacity ratio consistently exceeds R, F, greater than or equal to 2 for 1,000 exposures and R, F, greater than or equal to 1 for 100 exposures, regardless of model size. For instance, training GPT-2-20-16 on BIOS 10M for 1,000 exposures takes 8.5 days with 60 for a 100S, while GPT-2-12-32 on BIOS 20M for 100 exposures takes 2.4 days. Despite these findings, there is no need to scale up further. Instead, resources should be allocated to explore other aspects of the research. Figure 1 shows the scaling laws for GPT-2 models pre-trained on BIOS and data using FP16, mixed precision, for 1000/100 exposures. The peak capacity ratios consistently exceed R, F, greater than or equal to 2 for 1000 exposures and R, F, greater than or equal to 1 for 100 exposures, regardless of model depth/size. Models with R max, F, less than or equal to 1.8 attain near-perfect knowledge accuracies, indicating that for a dataset containing B bits of knowledge, selecting a model size P greater than or equal to B/1.8 is sufficient. Across all models, R, F, less than or equal to 2.3, reinforcing the maximum capacity across models and indicating that no model exceeds capacity ratio 2.3. The learned knowledge is also flexibly extractable via fine-tuning using QAs like what is Anya Forger's birthday, and can be further manipulated in downstream tasks. The authors train a series of GPT-2 models using a protocol called 1000 exposures, which ensures each piece of knowledge is presented 1000 times. This is different from making 1000 passes over the data. The initial findings show that the peak capacity ratio R, F, consistently exceeds 2, with models achieving near-perfect knowledge accuracies if R max, F, less than or equal to 1.8. Additionally, no model exceeds a capacity ratio of 2.3. The study also examines the impact of data diversity, finding that rewriting data does not hurt and may sometimes improve the model's capacity. Figure 2 illustrates the scaling laws for GPT-2 models trained on the BioD, N, K, C, D, L, T data for 1000 exposures. The peak capacity ratios consistently exceed R, F, greater than or equal to 2 with a wide range of K, C, D, L, T values. Models with accuracies less than or equal to 50% are excluded from this figure, but are included in Figure 12. The analysis concentrates on the 5 hyperparameters K, C, L, T, D, disregarding the influence of N. Each subfigure varies a primary hyperparameter while fixing the other 4, providing a detailed view of how each parameter impacts the model's capacity. Figure 12 illustrates the scaling laws for GPT-2 models trained on the BioD, N, K, C, D, L, T data for 1000 exposures. The figure demonstrates that across a broad spectrum of values, with K, C ranging from 1 to 50, D from 10 to 10,000, L from 1 to 50, and T from 20 to 40,000, GPT-2 models consistently exhibit a peak capacity ratio R, F, greater than or equal to 2. Each of the 4 subfigures varies a primary hyperparameter while fixing the other 4, providing insights into how each hyperparameter impacts the model's capacity. In this section, the authors explore the impact of insufficient training on model capacity. They consider scenarios where knowledge appears only 100 times during the pre-training phase. The authors calculate capacity ratios for models trained with 100 exposures on the BIOS N dataset. Their findings, summarized in Result 4, show that when trained for only 100 exposures on BIOS N, with N ranging from 10K to 10M, the peak capacity ratio R, F, consistently exceeds R, F, greater than or equal to 1 across a range of GPT-2 models. Although 1000 exposures may be necessary for a model to reach its maximum storage capacity, training with just 100 exposures results in a capacity loss of no more than 2x. This analysis sets the stage for further exploration of knowledge with extremely low or high exposures in Section 10. The paper examines several transformer architectures, notably Llama and Mistral, highlighting their differences from GPT-2. Key distinctions include the use of gated MLP layers, untied weights, and larger MLP layers in Mistral. Mistral also features group query attention and employs a different tokenizer and activation function compared to GPT-2. The study investigates whether these architectural variations affect the model's maximum capacities. Findings suggest that GPT-2, enhanced with rotary embedding and without dropout, performs comparably to other architectures in sufficient training regimes. However, in insufficient training regimes, Llama and Mistral may underperform GPT-2, especially when using gated MLP layers or removing all MLP layers. These results indicate that the 2-bit/param capacity ratio is relatively universal among typical language model architectures. Figure 3 illustrates the scaling laws for various model architectures on BIOS and data with 1000 exposures. It shows that all model architectures, including Llama, Mistral, and even models with reduced MLP layers, closely follow GPT-2's scaling law. The only notable difference is observed in tiny models, where tying the model's weights enhances its capacity. This indicates that the 2-bit/param capacity ratio is a relatively universal law among most typical decoder-only language model architectures. Figure 4 illustrates the scaling laws for various model architectures when trained on BIOS and data with 100 exposures. Notably, the Llama architecture shows a 1.3x worse capacity ratio compared to GPT-2, even after optimal tuning of learning rates. In contrast, reducing the size of GPT-2's MLP layer by 1/4 has a minimal effect on the capacity ratio. However, completely removing the MLP layers results in a significant decrease in the capacity ratio, more than 1.5x. These findings highlight the importance of the MLP layers in maintaining the model's capacity, especially in the 100 exposure training regime. Figure 5 provides a detailed comparison of the scaling laws for the Llama architecture with BIOS and data under 100 exposures. The key findings indicate that replacing the gated MLP in Llama with a standard MLP significantly enhances the capacity ratio, particularly for larger models. Additionally, for tiny Llama models, switching to the GPT-2 tokenizer is necessary to match GPT-2's performance, although this is a minor issue. Other modifications, such as changing activation functions or adding trainable biases, do not noticeably affect the capacity ratios. Figure 6 illustrates the impact of quantization on the capacity of language models trained with 16-bit floats. The key findings are that quantizing models to int8 has a negligible impact on their capacity, while quantizing to int4 reduces their capacity by more than 2 times. This suggests that for high-quality int4 models, incorporating quantization during training may be necessary to preserve capacity. In this section, we explore the effects of quantization on model capacity and scaling laws. Specifically, we examine the impact of quantizing models trained with 16-bit floats to int8 and int4 using the AutoGPTQ package. The results show that quantizing to int8 has a negligible impact on model capacity, while quantizing to int4 reduces capacity by more than 2x. This suggests that for high-quality models, incorporating quantization during training may be necessary. Additionally, we discuss where knowledge is stored within these models. Despite using 8-bit parameters, models can achieve a capacity of 2 bits per parameter, indicating efficient knowledge compression. This raises questions about the storage mechanism, which appears to be complex and not solely dependent on individual layers. The mixture of experts, MO, architecture is a key method to enhance efficiency in modern language models by incorporating sparsity. Despite having a large number of total parameters, the effective number of parameters used during inference can be significantly less. For instance, a GPT-2 model with 32 experts per layer uses 64 D2 total parameters but only 2 D2 parameters per token during inference, resulting in a parameter ratio of approximately 11.3. This raises the question of how this affects the model's capacity ratio. The results show that MO models are nearly fully efficient in storing knowledge, with a peak capacity ratio decrease of 1.3x in 1000 exposure settings and 1.5x in 100 exposure settings. This indicates that the MO architecture effectively leverages all its parameters despite the sparsity constraint. Figure 7 illustrates result 9, which shows that mixture of experts, MO, models are nearly fully efficient in storing knowledge, capable of leveraging all their parameters despite the sparsity constraint. Specifically, in the 1000 exposure settings, the peak capacity ratio decreases by 1.3x, and in the 100 exposure settings, it decreases by 1.5x. This result holds even in the sparsest setting where top equals 1 and cap factor equals 2 in the MO routing. The presence of junk data significantly impacts the scaling laws of useful knowledge capacity. When 7/8 of the training tokens come from junk data, the transformer's learning speed for useful data degrades significantly. For instance, with 100 exposures, the capacity ratio may degrade by 20x compared to training without junk. Even with increased exposures to 300, 600, or 1000, the degradation is still substantial at 3x, 1.5x, and 1.3x respectively. This highlights the critical importance of the quality of pre-trained data. In contrast, if the junk data is highly repetitive, it does not affect the model's capacity for standard knowledge. Finally, adding a special token to useful data can mitigate the degradation, improving the capacity ratios significantly. Figure 8 illustrates the capacity ratios of models trained with 7/8 junk data and varying exposures of useful data. It shows that the presence of junk data significantly impacts the capacity ratios, especially when the junk data mimics random knowledge. However, increasing the training time substantially can mitigate this degradation. Additionally, adding a special symbol token to the useful data, akin to domain names, greatly improves the capacity ratio, demonstrating that language models can prioritize learning from high-quality knowledge domains without prior knowledge. In this study, we investigated the scaling laws of language models, focusing on the relationship between model size and the total bits of knowledge stored. Our findings reveal a precise, universal scaling law. A sufficiently trained transformer can store 2 bits of knowledge per parameter, even when quantized to int8, which is only 1/4 away from the information theoretical maximum. We also examined how these scaling laws are influenced by various hyperparameters, including training duration, model architectures, floating point precision, sparsity constraints like Mo, and data signal-noise ratios. Our methodology provides a more accurate and principled playground for comparing model architectures, training techniques, and data quality. This playground can assist practitioners in making informed decisions about model selection, training data preparation, and further theoretical research into LLMs. Finally, our research represents an initial step towards addressing a fundamental question: how large does a language model need to be? We hope our findings will inspire further research in this area. Ultimately, we aim to provide a principled answer to the question: are language models with 1T parameters sufficient to achieve AGI in the future? Figure 9 illustrates the scaling laws for GPT-2 models pre-trained on BIOS N data with mixed precision, FP16, for both 1000 and 100 exposures, including one-layer transformers. The key observation is that one-layer transformers exhibit a slight deficiency in capacity ratio compared to multi-layer transformers, particularly noticeable in the 100 exposure setting. Despite this, the peak capacity ratio for 1000 exposures remains consistent with R, F, greater than or equal to 2, and for 100 exposures, it is R, F, greater than or equal to 1. This figure provides a comprehensive view of how different transformer depths impact the knowledge storage capacity of GPT-2 models. Figure 11 presents the scaling laws for 2 different biography datasets, BioSimple and BioR, both trained with 1000 exposures. The BioSimple dataset lacks sentence diversity, meaning each individual's knowledge is stored in a fixed ordering of 6 fixed sentences. This lack of diversity results in a slight decrease in the capacity ratio compared to the BIOS dataset. On the other hand, the BioR dataset is generated by Llama 2, which introduces semi-real human biographies with diverse paragraphs. The capacity ratio for BioR data also shows a slight decrease, particularly for larger models, likely due to the inclusion of irrelevant details that consume model capacity. These findings suggest that data diversity, even if it introduces irrelevant information, can enhance the model's capacity. Figure 13 provides a detailed breakdown of the knowledge components within the parameterized BioD scaling law experiments. It specifically focuses on the percentage of bits attributed to name and diversity components, as defined in equation 8.1. This breakdown helps in understanding how different hyperparameters impact the overall bit complexity lower bound. The figure emphasizes that while the value component typically dominates, the name or diversity components can become significant under certain settings, highlighting the importance of considering all 3 terms in the lower bound calculation. This analysis is crucial for validating the lower bound established in Theorem 3.2 and for understanding the nuanced contributions of each component to the overall complexity. Figure 14 demonstrates the impact of quantization on GPT-2 models trained with different exposure settings. Panels A and D show the original scaling laws for 1,000 and 100 exposures, respectively. Panels B and E illustrate the scaling laws after quantizing the models to 8-bit, revealing minimal impact on the capacity ratio. In contrast, panels C and F show the scaling laws after quantizing to 4-bit, which significantly reduces the capacity ratio by more than 2x. This indicates that while 8-bit quantization maintains model performance, 4-bit quantization severely compromises the model's ability to store knowledge. Figure 15 illustrates the impact of 8-bit and 4-bit quantization on GPT-2 models trained on BioD, NK, CDL, T data for 1,000 exposures. The left panel replicates Figure 2, displaying models with accuracy greater than or equal to 50%. The middle panel shows the results after quantization to 8-bit, revealing minimal changes in model capacities. The right panel, after quantization to 4-bit, demonstrates a significant reduction in capacity, particularly for models with large D and L values, which accounts for the missing columns in Figure 15I. This observation underscores the substantial loss in model capacity when quantizing to 4-bit, especially under conditions of high diversity and long sequences. Figure 16 illustrates the scaling laws for GPT-2 models enhanced with a mixture of experts, MO, architecture, specifically with 32 experts, on BIOS and data. The figure highlights that while MO models significantly reduce the number of parameters used during inference, they also lead to a degradation in capacity. Specifically, the 1,000 exposure capacity is reduced by 1.3 times, and the 100 exposure capacity is reduced by 1.5 times, compared to standard GPT-2 models. This reduction in capacity occurs despite the MO models using only 8.8% of the total parameters during inference. The results underscore the trade-off between parameter efficiency and knowledge storage capacity in MO architectures. Figure 17 illustrates the scaling laws for GPT-2 mixture of experts, MO, models with 32 experts, specifically focusing on the BIOS, and data for 100 exposures. This figure provides a detailed comparison of different configurations, such as top cap factor equals 1, 2, 2, 1, and 2, 2, highlighting minimal differences among them. Notably, the configuration 2, 2 performs best for deep models like GPT-2-16-4 with 32 experts. This figure serves as a complement to Figure 16, offering deeper insights into the performance of MO models under different settings. Thank you for watching.